Hello and welcome to the Avid Technology Podcast with me, Ryan Morn. I'm really excited about today's episode. We've got a fantastic guest on the show. He is the Principal Fellow of Advanced Propulsion at Warwick University in the Warwick Manufacturing Group, sometimes known as WMG. It's a guy called Ian Goodman, and Ian is an expert on electric vehicle battery systems, having been involved in the space for many, many years, since before it was fashionable. And you know what? He's really just a super nice guy. So without further ado, it gives me great pleasure to welcome Ian to the show.
So Ian, thanks for joining us today.
Thank you, Ryan. Thank
you. So I guess to get straight down to it, how about, because back, when was it that you first got into battery systems?
I suppose I started battery systems generally about 30 years ago, but lithium battery systems, only probably about 15 years ago. And it was...
what were you thinking?
I know, yeah. So it was something that had just sort of captured my imagination, that everything I'd been doing before sort of paled into insignificance in terms of power and energy density. And it was just that just opened up a massive number of opportunities. And that was that happening, and building a couple of battery packs and trying out some design ideas was really the impetus to set up, my wife and I, to set up our own business.
Wow. And I mean, of course, back then, so I always tell the story, that I set up Avid before electric vehicles were cool. And so back then, we're talking the pre-Tesla years, like early days of electrification. So it was not a cool thing to be involved in at all. What were you thinking electric vehicles, or was it sort of were you just interested in batteries and energy systems, or did you kind of see what was going to happen?
No, it was very much electric vehicles. And what actually sort of kicked it off, and especially my wife and I deciding to put our life savings into a business, was we watched a couple of films, An Inconvenient Truth and Who Killed the Electric Car. And those were, the ideas had been percolating in the background for a couple of years, and it was, and I couldn't have done it without my wife's support. And we watched them and they said, well, this is it. This is what we're going to do now. We're going to try and make a difference. And that was the real sort of start of it. And, whilst, it had a massive passion for electric vehicles and had been building them for a long time, that was the moment of truth that we said, okay, we'll put our money where our mouth is, kind of thing.
You make it a business. And back then it wasn't, I know, because we were back then as well. You couldn't go out and buy anything. Like nothing existed.
No.
Cell suppliers weren't really. Yeah. So how did you go about actually getting started?
So I through the internet, I picked up a few contacts in Taiwan, and with a fair chunk of our startup money, I started traveling all across Asia.
Right.
And doing everything from speaking at conferences to trying to validate supply chains and speaking to cell manufacturers, and really using my engineering understanding to try and work out whether they were going to be a good manufacturer and they were going to last. And I wasted a lot of time, but that I really did waste a lot of time.
So was that because you found...
what they say, there are liars, there are damn liars, and then there are cell manufacturers.
As opposed to battery system integrators.
Yes. So I spent a lot of time and a lot of traveling, and I made a few contacts really quickly that allowed us to pick a nuts and bolts assembly technology that we could adapt very easily for any particular shape and a lot of different applications. And there is no one size fits all cell, but we found something that was kind of middle of the road, reasonably powerful, and we could actually provide solutions. And that's what really kicked it off. And we could actually start selling product, but very, very quickly realized that you had to provide a complete solution. So we then spent the rest of our seed money on developing battery management systems and systems integration technologies. And we grew from starting in late 2007. By 2010, we had 30 staff, and we're generating a couple of million revenue a year.
Wow.
And had done some really prestigious projects.
So who was kind of actually, first question, what was back then, what was the kind of cell technologies that you were seeing? Was it PO4 or was it something?
Yeah, the vast majority of it was LiFePO4, lithium iron phosphate, and there was NMC and NCA technologies around, but customers we were working with had seen how badly things go wrong with those technologies when they go wrong.
Yeah.
And LiFePO4 is much more benign. So we just didn't get asked for it very often. And when we did, it was always down to mass. You had to have the absolute lightest battery. And
so then you would go for the more racy NMC or NCA chemistries.
That's it. And your pack development time on those technologies, because you had to do a lot more around safety and you had to do a lot more testing and validation work. It was expensive.
Right.
And everyone balks at non-recurring engineering costs. And even now, it's considered, these are made in their millions. Surely they should be $100 a kilowatt hour, because that's here on Bloomberg. So, the reality obviously is very different. So, yeah.
And did the LiFePO4, did that stay the dominant kind of chemistry for you, or did you see it shift as the others started to improve and become more stable and more understood? Was there a timeline there?
So I would say until about 2013, LiFePO4 was pretty much the vast majority of the chemistry that we sold. And it wasn't until about 2013, 2014 when there were a number of manufacturers that started producing chemistries where nickel manganese chemistries that actually gave you a level of safety you could cope with, and there were very predictable ways in which they failed. Yeah. So that means you can then design a battery management system that deals with that, so they never get to that failure point.
Yeah.
And we were getting a lot more sophisticated in our analysis and our testing, which gave us a lot more confidence in selling the product. And towards 2015, I would say LiFePO4 was probably only about 20% of what we sold, and that was much more into energy storage rather than automotive. There was a big chunk of the early business was automotive, and that technology that we developed there sort of ended up swinging into energy storage, and we sort of did a bit more LTO as well, titanate. But yeah, it was the NMC type technologies that really took over in automotive.
Yeah. So what was in that kind of period? I don't know. Could you say what your kind of typical project looked like? What kind of customers were coming to you?
I can honestly say there wasn't a typical customer.
Right.
And if you wanted variety, that was the business to be in, because we'd have in a week a couple of automotive projects. One might be in a truck, might be in a passenger car. You'd have a couple of robotics or energy storage. We used to get ones completely off the wall. We had someone wanted to have 100 kilowatt hours of battery on the bottom of the seabed to run a load of sensors, and we had to design it inside a pressure vessel. And that's the great thing about batteries, I think, from an engineering standpoint, is that everything uses them.
Yeah.
So that it is, if you're a battery systems engineer, you span every industry.
Yeah.
And there's lots of opportunity.
Yeah, and I guess now, as the functionality or the performance of the batteries is getting better and better all the time, and the costs are coming down, actually you're seeing them in more and more different applications. So it's now, doing grid reinforcement and fast frequency response is that's a recent, and obviously electric vehicles and all sorts of robotics and warehouse equipment, and it's a huge, massive transition of technologies that really it's all about the battery. The battery's the enabler, isn't it? You know,
it is. That's it. And you can do a lot with a battery to solve problems outside of the battery. You know, whether that's the cooling system or whether it's the traction system. You know, there are ways you can tweak the battery that help problems elsewhere. So a lot of the work we were doing ended up being, touching on every element of the full system.
Well, so that's quite interesting, because there's this sort of principle in the market. You've got various different strategies from different manufacturers. So I'm talking the automotive market now, and you've got some companies where they're saying, right, we believe that this is all about the battery, and if we want to do electric vehicles, we need to have an in-depth understanding of the battery. We need to own that supply chain, and basically have our own sort of capability, right from cells to full packs. And then you have other companies saying, we want to make cars, we don't want to make batteries. That's not our core competency. We don't want to do that. In terms of a strategy, would you see? You know, what do you think is the best? What do you think is going to work and give?
How deep are your pockets, Ryan? That's what it comes down to.
Mine aren't very deep. And I've got even shorter arms.
What Tesla have done is the only way they could have made the Model 3 and make it profitable. And I do think that every other manufacturer is going to struggle to have the pricing that the Model 3 now does and be profitable without that fully integrated, top to bottom supply chain.
Yeah, I mean, I don't disagree. It was interesting though seeing recently. So Nissan, who obviously have been a big leader in this, and there's a couple of, hasn't quite happened yet, but it is in the public domain that they're selling their battery business. Yeah, which seems like that seems like a backward step from where the conclusion that others seem to be making is they're getting to we need to have more control over this, but they're kind of stepping back from it.
Yeah, and I think that's basically a function of, as I said earlier, there is no one size fits all battery.
Right.
But the battery technology they've got there is just one size. It isn't flexible. It is just one mechanical assembly, and it won't work in every application. So I think what they're probably doing, and I have no inside information on this, but my external view is that they just want to be more flexible at where they are at the moment. Yeah. And I think nobody's late to the party on this. There's plenty of time, and the way the amount of time it takes to go from a proven chemistry in the lab to being commercially viable is a long time, and things do move slowly in the battery industry. Manufacturing, it moves very, very fast. The ramp rate on cell manufacturing is phenomenal, but it takes a hell of a long time to get to that point where the cell's ready to be made in its millions.
Yeah, it does, and it always strikes me that cell plants are so dependent on utilization that it's they're quite eerie, really. When you go in a cell plant, there's not normally a lot of people around, and there's a lot of very expensive machinery. The people that are around tend to be wearing face masks and actually, I was going to say face masks and lab coats, but not even face masks and lab coats. It's the full Mars exploration gear inside the cell plant. So it's a little bit spooky because you can't tell who anyone actually is and can't really hear what they're saying properly. And there's all this very, very, very expensive equipment processing. It's just the most mind-boggling rates of thin sheets of material that are flying around everywhere. And bringing it together into cylindricals or into pouch cells. But the trouble with that kind of plant is, if you're not running it at 100% capacity, it's costing you a huge amount of money in terms of slack capacity. So it's a very difficult balance in terms of the costs and the capital expenditure on the plant and how much you think you're going to sell and how that's going to all balance out, I would think.
Yeah, and I think what Tesla did is they picked a company, a partner to work with that were absolutely the top of their field when it came to chemistry in that particular form factor, and then bet the farm on it. And rightly or wrongly, it's got them to where they are now, and I don't think they could have done it any other way. I remember about 2013, walking around the first BYD battery factory and having a tour there.
Yeah.
And the scale of it, even then, was enormous. And they showed us their quality control area and the timing of every aspect of it. And it wasn't running to full capacity, but we worked out, my colleague and I, that it had probably about 3.2 gigawatt hours of capacity.
Yeah.
And when you see them put 300 plus now kilowatt hours in a bus, you can understand why they need that. And they're selling a lot of buses all over the world now. And the partnership they have with is it Alexander Dennis?
Yeah.
Yeah.
In the UK,
so in the UK and a few others around the world, they had to do that. They had to take control.
Yeah, they were often. They're very, very different companies in terms of how they look, sort of from the outside. But actually, BYD and Tesla have a lot of similarities in that they are both kind of gone for the we're really a battery manufacturer, or I think Tesla say they're something like a vertically integrated energy company or something.
Yeah, better
marketing speak than I could ever come up with. But when you look at it, BYD make batteries and they sort of wrap vehicles around them. And Tesla have sort of done the same. It's a different philosophy there from someone who's a car manufacturer who's then going to go out shopping for a battery to suit the car. Really, you could argue that Tesla and BYD have produced cars to suit the batteries. Yeah. So sort of the other way around. And maybe...
But it makes the most. It makes the most of the battery. And when you think is the single most expensive component on the vehicle, why wouldn't you do that? You try and wring every little watt hour of value out of that battery to enhance your vehicle.
Yeah, definitely. So on that, I know there's a lot of the projects that you've worked on that you can't talk about because they're just too top secret and military stuff and all that kind of. But what was the best? What was the most exciting project that you ever worked on? Can you tell us?
I think doing the Foxhound project was something that we were really proud of.
Right.
And it was, as a business, it was the first big, multi-million-pound deal. And it was, in simple terms, we were replacing lead-acid batteries.
Yeah.
But it was going in an incredibly harsh environment. We had to massively reduce the size. We had to make sure it would heat itself up and cool itself down without any kind of intervention. And it had to be, from an EMC point of view, it had to be electrically completely silent.
So just for those who don't know, what was Foxhound?
Okay, so it's the British government's replacement for the Land Rover for the army. So they've been using Land Rovers for 30-odd years, and they replaced it about 5 years ago with the Foxhound. And it had a V-shaped, it was a composite body and a V-shaped hull. And obviously a lot of our soldiers had been dying with through IEDs and vehicles being blown apart.
Yeah.
And the shape of the chassis underneath a Land Rover was such that if you were inside that vehicle, you had a 90% chance of dying in an IED, whereas with the Foxhound and the V-shaped hull, you had a 90% chance of surviving.
Right.
And it really sort of changed the face of patrolling with these vehicles. It was so much safer.
So then, designing a battery that was going to go into something that was being designed to be resistant to being blown up. That is literally like bomb-proof.
Yes.
So
yeah, it was, and it was heavy, but it was very compact, and it would, it was designed to last, thousands of cycles, and in very harsh environments, and when it's sitting next to the equipment that's trying to detect, mobile phone signals, 100 kilometers away, it has to be completely silent. So I think we got Land Class A certification, and we were the only company ever, and I think even to this day, it was only battery ever that achieved Land Class A EMC certification for a military application.
Wow, super quiet.
Yeah, and it was our kind of first big production run as well. Subsequently we did do thousands of units, but at sort of 400 plus units of a 65 kilo battery. That was our big one. And obviously, with it, the battery itself was powering equipment that was saving lives in a vehicle that was saving lives. I suppose that's a proudest moment.
Yeah, and I know. Some of the batteries you've done for some supercars, and there's some pretty exciting things that are still like absolutely the best that you could imagine that have got batteries that you designed in that are kicking around today. So it's And then, so you business-wise, you took the decision to go from being an independent company to joining a larger group.
Yeah. So I did help found a larger group, which unfortunately wasn't particularly successful. But my wife and I were a little battle worn after 8 years of running our own business. So we kind of stepped out of the management, and I just focused on R&D for that company, and that was a lot of fun for 18 months. Just got 18 months playing with batteries and developing new technologies, and that was really nice. Yeah,
fantastic. And then. So now, with Warwick, it's a fantastic role, and they're really they're the centre for. They've got the battery manufacturing centre there, and they've got lots.
So
of expertise.
I think it's the Energy Innovation Centre.
Okay.
So, and it's about £60 million worth of battery testing toys. From my perspective, it's an amazing place. It really is. It's fantastic.
And what do you? That as well would give. Well, I guess your experience in the past, but then the stuff you're doing now, you must see an awful lot of different EV programs and people doing battery systems and stuff. What are the main? Do you see like the main challenge, or are there problems that repeat themselves over and over and over again that you just wish you could say, don't do that, or is every single one different?
They are all different, but you're also right in that it's always the same challenge every time. Is can we make it safe?
Yeah.
Safe to assemble to start with, safe to operate, and then safe in a crash.
Yeah.
How can you get it to last the life of the vehicle?
Yeah.
Thermal management, and that is the key to a long life in a battery.
That's good to hear.
Yeah, it is. We did have a lot of projects where batteries were treated as throwaway. No one really worried about degradation because the role that they played in the project and their cost was inconsequential to failure.
Right.
It had to work, and if that meant changing the battery out every 500 cycles, no one cared.
Yeah.
But of course, when it comes to passenger vehicles and buses and what have you, the battery has to last as long as possible.
Because it's such a huge impact on the total cost of ownership for the vehicle. Yeah. So then, did Warwick get involved with companies where they're trying to work out things like life cycle or how to, sort all these manufacturing issues out? Is that?
Yeah, so a lot of the work there is done on developing models of cells and understanding how they degrade, and how those cells not only degrade, but what's the worst case scenario for that cell. So even if your thermal management is limited, you can work within an envelope that actually still gives you the lifetime that you need.
Right.
And they've got some incredibly sophisticated techniques and equipment, and some very, very clever people, far cleverer than I. I'm already, you give me the data and I'll design you a battery.
Yeah.
But actually working out the data, that's not my bag. But and it is the centre of UK battery engineering. You do see some amazing projects coming through, and you get to, my role is to support those projects in system engineering and trying to meet a customer's requirements, whether that is just give me a megawatt of power for 30 seconds, and that's all you're going to do all day,
right?
And then, or as we're doing in some projects at the moment, it's very transient duty cycles, but very predictable.
Right.
So you end up pre-cooling the battery before the discharge event, because you haven't got enough cooling capacity to do it afterwards. So you have to do a bit before and the rest of it afterwards. Yes.
Oh, wow.
It's interesting.
So it gets into the kind of control over at the system level.
Yeah.
I remember going around Warwick a while ago, and they used to have some labs where they were doing quite amazing to see tests, but it was sort of I don't know what I'm going to say. Dangerous. That's probably not the right word, because obviously by the time university
Do you
health
mean-
and safety have had their way with it, it was not dangerous at all. But it was certainly
No.
spectacular. Are they still doing that sort of fundamental?
The abuse testing, and that's become a really big part of the work they do for OEMs.
Right.
Because of course that they need to understand fundamentally how a cell fails, so that you can design a system and a car around that protects the battery. And if it can't protect it, they have to understand how the cell fails, so they can mitigate that risk of failure. And of course, it all eventually feeds into NCAP ratings for passenger vehicles.
Yeah, because obviously people are not wanting, battery fires are a big problem if they happen. So preventing battery fires is a massive.
Prevention is far better than dealing with it.
Yeah. Do you think? I remember years ago, the cells were really difficult to handle, and actually the slightest little thing you could end up with a thermal incident with a cell. Do you see that the sort of cell technology has improved even for these very energy dense? So they're just easier to deal with?
Yeah, massively. And also, I think, going back 10, 15 years, people didn't understand the risks and were very blasé about it. Now, the health and safety is much, much stricter. So these incidences just don't occur. And actually, the technology has become far more energy and power dense. So, the potential for failure, or shall we say, the potential of a thermal incident, should it occur, is significantly higher than it used to be.
Yeah.
It's actually far more difficult to cause it now.
Right. Yeah, just basically the designed out at the cell level to some of these things.
Yeah.
What are the big? So then it's sort of looking forwards. What do you think are going to be the trends, and where do you see people putting all of their effort and research moving forwards?
So there's always, there are new chemistries coming along and tweaks to chemistries coming along all the time. Right. But if you can prove a chemistry at the coin cell level in a lab, it could take you 10 years to get it scaled up and proven, where you can build a gigafactory.
10 years? Wow.
Yeah.
Wow.
It could. Yeah. I mean, I think the quickest it's ever happened was about 5 years, and even then, that was only with the support of an OEM that said on day one, okay, we'll buy 1 million cells.
Yeah.
And they just kept adding a zero to that as their business grew. So it does take a long time, though. There are a huge number of steps to go from that coin cell to producing a cell of the size that you would see in an electric vehicle, whether that's a 21700 or a pouch cell or one of the larger cylindricals.
And is that, of the chemistry stuff that's coming through, is there any kind of game changers there potentially, or is it very much incremental?
I've thought this for about the last 10 years, that lithium battery technology is going to grow. They're going to get better and better, and then there will be something that takes over massively. I don't think there's a short life in batteries. I think they have a very long life. I can't imagine there will be a game-changing technology in the next 10 years.
Right.
But beyond that, I'm pretty sure it's out there somewhere. I don't know what it is, but there will be an energy storage. There'll be an energy storage solution that is, a fraction of the size of the technologies we have today. But I think where we are today, commercially available 250 watt hour per kilo cells that are easy to manage, and you just look at the Model 3. I keep coming back to Tesla, but you look at the Model 3 battery.
Yeah.
And it's a very clever design, and I fully expect that battery to be operational for 200,000 miles. There's no reason for it not to be, and the evidence, all the evidence on the Model S batteries point to that as well. Even though there are different cell size and tweaks of the chemistry.
Yeah, because there's kind of two strands, isn't there? You've got like the fundamental chemistry, not lithium, new stuff coming, potentially, maybe some things in the wings. And then you've got the tweaks on lithium, but with standard kind of wet electrolyte construction methods.
Yeah.
And then solid state.
Yes. Yeah.
So,
So I'm really excited by it.
You didn't sound excited.
But I am really excited by it.
Yeah.
But I'm also frustrated
Right.
that I can't actually go and buy any yet. You know, and you have a lot of companies out there saying, "Oh, we're going to have solid state in our vehicles in 2020 and 2021," and I don't know everything. I really, really don't. But I'm not seeing any evidence of that in the market. There are a couple of companies. There's one in the UK that do coin-size solid-state cells.
Yeah.
That going ECUs. That's the only solid-state cell I know you can actually go and buy. You know, even as an OEM with a big fat checkbook. You know.
Yeah. I kind of wonder if some of the announcements might be because within solid state there's kind of two sorts of solid state. Well, you've got proper solid state basically, so ceramic, micro deposited layers, nanotechnology, good stuff. And that's the kind of really promising, groundbreaking stuff, which is very difficult to commercialize at scale because
yes, phenomenally difficult. And I have been involved just on the peripheral of some of that stuff, and it was very, very challenging. You know, and the main thing with solid state is about the safety. That's what's seen to be the big breakthrough is safety.
Yeah,
not necessarily the whole energy density, power density thing.
Right.
Yes, it is suggested, and all the evidence says there will be significant improvements, but we're not at the point where the fuel tank on an internal combustion engine size gives us the range in the battery. I mean, we're nowhere near that comparison. Yeah. Even with solid state.
Do you think the safety thing is that basically driven because of in a solid state you get rid of the wet volatile solvent in the electrolyte?
Exactly. Right. Yeah, and you have nothing to leak.
Yeah, and
it's the leakage that catches an ignition source, and boom, off you go.
Yeah. So that is in case anyone sort of wondering about that, in a cell you've got basically layers of very thin sheets of material. You have an anode and a separator and a cathode, and they're like fractions of a millimeter thick sheets that are either stacked up in layers or wrapped around in a big coil. And then there's an electrolyte, which is a solvent basically. So imagine kind of whiteboard cleaner with lithium dissolved in it, lithium salts, I think. And some of the safety with the battery safety stuff comes from essentially if you get a short circuit inside the battery and the battery gets a bit hot, then that solvent starts to break down, and because it's a very volatile liquid, it combusts or goes on fire very easily. But the solid state batteries, they don't have that liquid electrolyte anymore, so you can still have a short circuit in the solid state battery obviously, but then there's nothing there to catch on fire other than the housing and case of the battery itself. So the safety's potentially massively improved because of getting rid of that nasty volatile liquid electrolyte.
Exactly what he said.
Yeah. And the other kind of batteries that
very well explained, Ryan. That's really well explained. Thank you.
Well, I'm doing that now because I know if I didn't do that, I'd get a question about it later. So I'm heading that one off at the pass. The other kind of batteries, which is it's a grey area for me, and I don't know what you think of this. So I've seen some people describing solid state batteries, and basically they're not properly solid state batteries. So they've got a kind of a non-liquid electrolyte, so sort of gel or
yes, I know what you mean.
Semis. So in some industries they're quite widely used, those batteries, aren't they? Would you class that as a solid state battery or not? Or?
I don't know that I do, but it's a long way in that direction.
Yeah.
And I always think of it like Wrigley's chewing gum kind of layer. That's that becomes the layer, and when it's not actually solid.
Yeah.
At the same time, it'll kind of hold its shape, and I think that technology is far nearer to market.
Yeah.
But again, you still can't go out and buy them commercially yet.
I just wonder if maybe that's what some people mean when they're saying solid state, if they're talking about these sort of semi-solid batteries. But I guess we'll see, because it's pretty big companies. I think the biggest one I can think of that's been talking about launching solid state batteries is Daimler. So they came out with some publicly and said they're near with solid states. I think it was an electric. Was it electric truck launch or an electric bus launch? It was a commercial vehicle, which is interesting that they tied it in with a commercial vehicle launch rather than a passenger car. And they came out and said, and by the way, by 2022 or something, these will all have solid-state batteries in, which is quite a brassy claim.
Yeah, but I think I can understand why that application, because it's going to be a very large battery.
Yeah.
So the power requirement and the C rate on the cell, the amount of power density you need of that cell is probably going to be reasonably low.
Yeah.
So you don't have to have an amazing performance from these first cells that they're producing and putting in the trucks. I mean, that would be my guess.
Right.
Why they chose that application, because they're going to be putting 250, 350 kilowatt hours in there to give it meaningful range.
Yep.
When actually they probably only need 250, 350 kilowatts of power.
So it's working with 1C.
Exactly. So where even you look at the Leaf, it's 21 or 22 kilowatt hour version. It had to produce 80 kilowatts or more. Yeah. So that's a 4C cell, and that thermally is a very, very big difference.
Yeah, so this is the challenge. We've talked about this before. So basically in the batteries, like I said before, you've got the layers of material, and to get the energy density up, people have thinned it out to give more active surface area in a particular pack, and the solid-state stuff is taking that to a whole other level in terms of like depositing material with sputtering and all sorts of clever techniques. But then when you thin it all out, it can't carry the current anymore that the less energy dense battery could. So it is a big challenge with solid state. That the material is now so thin, so that's great. You've got massive active surface area inside the battery, but then you can't deal with high current flows because it's essentially very low cross-sectional area of the conductors inside the cell. So it's
and it's always a compromise. Every cell that's ever been manufactured and goes to manufacture is a compromise between energy density, power density, and the volumetric limitations.
What do you think of supercaps in terms of that and Tesla buying that supercapacitor company? Was it Maxwell?
Maxwell, yeah.
So do you see a useful role for supercaps in the EV kind of battery systems?
So nothing that's immediately obvious, and I kind of it's probably in there some way in some kind of enabler. That I think is probably their thinking behind that acquisition, is that they see it as an enabling technology for something else. And whether that's as a grid buffer for their supercharging network, or they are changing their inverter technology and they're going to use supercaps, I don't know. But I have worked with supercaps on as a part of a battery system with some power electronics between the two.
Yeah.
And whilst that in and of itself was very successful, it was incredibly expensive. Having that extra set of power electronics in there, and it was always very difficult to justify the project when you can go and buy a 200C cell that gave you the power density that you needed. But I don't see them in passenger vehicles. I think in trucks where you need short bursts of incredible amounts of torque, I see that there's possibility there.
Right.
Definitely. But again, for me, it's always about the commercial viability of the product. What's the justification for adding that complexity? Is it that now you get 10 years out of your battery instead of 5? Then you might well do it.
Yeah. It's they've been one of those supercaps have been on kind of the periphery for a while, and there's lots of things coming and potentially coming, but yet to see that really make a big dent. So it'd be interesting to see what happens there.
The energy density is just way too low to be any practical use, I think, in an EV.
Yes, not your primary energy storage.
No, definitely not.
No. So any other kind of trends that you see, or things that you see coming up in your work?
So there's a cell format that I think is now used in the Zoe, and it is in the I-Pace, that is a a pouch cell that, rather than having the terminals, the tabs along one edge, are now at opposite ends of the cell.
Right.
And what that creates is a thermal path, from an electrical path and a thermal path from the cathode to the anode. And these cells are generally, they may be 7 to 8 millimeters thick. They may be about, I've seen some up at 150 millimeters wide. Most of them about 100 millimeters wide, and then up to 300 millimeters long. So they're a long, thin pouch with big tabs on the end.
Right.
And what that effectively means is that when you're passing current through that cell, it's got a direct sort of, in layman's terms, a line of sight path.
Yeah.
Right the way through the cell. And because that's the direction of the current, you don't get any hot spots or any cold spots in the cell itself. And when you look at the cell, when you're working it hard underneath a thermal imager, it's all one color.
Yeah.
Whereas the traditional cells, where you have two tabs at one end, where you have the bit of cell between the two tabs is always hot, and the corners down at the bottom are always cold, and that's terrible for degradation. Really terrible. The cells die very quickly if they're not at an even temperature. So that cell format change dramatically improves the thermal performance of the cell, and actually makes it really easy to dissipate the heat as well.
Ah, interesting. There's the 2 camps, or 3 camps, 4 camps. So cell package. So you pouch that's really interesting in terms of pouches, isn't it? And that pouch cells are kind of being used in a lot of new applications. So a lot of the new cars that are coming into the market now, and trucks and buses and pouch cells. You've got the prismatics, you've got the sort of semi-prismatics, but then you've also got the cylindricals. And there's a sort of 2 big schools in terms of cylindrical versus pouch. But that sounds like, to me, what you just described of that pouch cell, that kind of sounds like a pouch cell trying to be a long, flat cylindrical. Yeah,
and that's always been the advantage of cylindrical cells.
Right.
That direct path meant that, especially 18650s, which are used by Tesla in the 21700 variant, created a very even thermal performance of the cell.
Yeah.
But cylindrical cells aren't the most volumetrically efficient packaging. So pouch tended to win in battery design circles, simply because they were much easier to manage the construction, and you kind of just dealt with the thermal inefficiency of it.
Right.
Whereas now this new cell format actually is really, really easy to package, and gives you a very simple thermal management system.
Right.
Far simpler than the one you see in the Tesla vehicles.
And do you think that would get over? Because one of the other big advantages with a cylindrical compared to a conventional pouch is they're really easy to handle. Like you just like a machine gun, the cells are going in, the bus bar arrays are being welded on both sides at once. They're really easy to handle and work on, and the speed at which they can be processed for manufacturing from a cell into a pack is huge. With a regular pouch, they're basically a bit of a pain in the backside to handle, and
they are. I think when you look at it at the megawatt scale,
right,
how many pieces you actually have to process.
Yeah,
I think probably on balance, the 21700 still wins, but there isn't that much difference. And I think the reason that the takt time, or however you describe it, for the cylindricals is as low as it is because there is a huge investment into making them very, very quick to manufacture packs. And I think if some of that investment, and I'm sure it will, moves over to the pouch cells, and the automation techniques were developed, you get to a similar pricing, manufactured cost,
and
with a smaller, more thermally efficient system.
Right. Yeah. So that new pouch design, though, that's going to get, I would think, get over a lot of these issues. It's funny, I saw yesterday there was a company, or something came up on my social media. It was about a company advertising flat wine bottles, and it was to do with.
Isn't that a wine box?
Yeah.
Been run over.
Well, yeah, it was like it's a flat wine bottle, and it's to save on shipping because you reduce the volume of the box significantly by going from 6 round wine bottles in a box to 6 flat wine bottles in a box. And I saw loads of people saying, "Oh, hasn't this been done before?" And I said, "Oh,
wasn't gin
brandy,
yeah, they all come like that, don't they?"
Yeah, stuff that you needed to take with you, basically stuff down your pants. Sorry, that was maybe too much from my youth. But flat bottles of wine that's the sort of similar comparator to packaging cylindrical cells versus packaging these larger capacity pouches where you just get that much better just utilization of space.
What about makes me weird packaging alcohol compared to packaging?
Yeah, well, yeah.
That works for me.
Yeah. What about prismatics? Where are they? Because some manufacturers are still sticking to prismatics, but do you see them having
they have their
future?
advantages, because that's what was always good about tabs on one edge of the cell is that they're all facing up, so you're only actually welding on one surface.
Right.
So they have that advantage. They're also a very rigid, self-supporting structure, like a cylindrical, unlike a pouch.
Yeah.
So it's quite a straightforward manufacturing process, and it does depend on what you're doing with the vehicle. If it's a hybrid where you've got high C rate, regenerative braking and acceleration events, you need something that's got is very thermally efficient. Whereas if you've got a battery electric vehicle where you're charging overnight and you're using it, in the 2, 3, 4 hours a day you're driving, there's nowhere near the thermal stress on the cell. So you don't need the most efficient method of thermally management. But there is no one cell for every application. But I think there are certain formats and certain cells that lend themselves very well to particular applications. Yeah.
Right. Interesting. So I've just noticed the time, and we need to wrap up, actually, otherwise one of us turns into a pumpkin. I'm not sure who. So thanks so much for joining us, Ian. It's been really interesting. And for everyone who's listening, I really hope you've found some value from that and that you've enjoyed today's podcast. If you could share this podcast with other people to help them learn more about the technology behind vehicle electrification, that would be great. Leave us a rating or hit like, and don't forget to leave a comment depending on which platform you're listening to us on. They all seem to work in different ways, but we really appreciate your support, and look forward to speaking to you again soon.